Hello everyone, welcome to another lecture of the course Digital Signal Processing. In the previous lectures, we had seen the concept of discrete Fourier transform. We have seen an example of how to find the discrete Fourier transform as well as the inverse DFT, and we have seen the periodicity and modulo operation for this DFT operation. So now let us consider another important aspect for this DFT. Now when we go for frequency domain representation, so it becomes necessary to understand what happens in frequency domain when we multiply two DFTs or two frequency domain representations. Now when we consider the Fourier transform or the discrete time Fourier transform of two signals, that is x1 of n, having the discrete time Fourier transform as x1 of omega and this x2 of n, having the discrete time Fourier transform as x2 of omega, then when we linearly convolve these two signals, that is x of n convolved with x2 of n, it leads to its equivalent frequency domain representation as simple multiplication of the two discrete time Fourier transform, that is x of 1 into capital X of omega. So capital X of omega, x1 of omega into capital X2 of omega. So we have this convolution in the time domain, and we get multiplication in the frequency domain, and we know that this is much more easier than finding the convolution, which is a complicated calculations. So now let us look at what happens when we multiply two discrete Fourier transforms of these two signals. So let us now try to find out what we get in the time domain when we consider this x1 of k into x2 of k. So we will consider the two signals x1 of n and x2 of n, and let them have the discrete Fourier transform or the n-point DFT as x1 of k and x2 of k. So we have this x1 of n having the n-point DFT as x1 of k, and this x2 of n will be having this n-point DFT as x2 of k, and we know that x1 of k can be given as summation n running from 0 to n minus 1 x1 of n into e to the power minus j 2 pi k n by capital N, and similarly this x2 of k can be given as summation n running from 0 to n minus 1 x2 of n into e to the power minus j 2 pi k n by capital N. So one point to be noted here is for both the signals x1 of n and x2 of n, we are finding n-point DFT, that is the value of n for both the signals is considered to be same. So now let us consider a discrete Fourier transform, that is x of k, given as x1 of k multiplied by x2 of k and let its time domain equivalent be given as x of n. So we have this x of n having the n-point DFT as x of k, and therefore using the synthesis equation, this x of n can be given as 1 by n summation k running from 0 to n minus 1 x of k into e to the power j 2 pi k n by capital N, And we know that this x of k is equal to x1 of k into x2 of k. So we have x of n is equal to 1 by n summation k running from 0 to n minus 1 x1 of k into x2 of k multiplied by e to the power j 2 pi kn by capital N. Now if we go back and look at the value of x1 of k and x2 of k, so we have it equal to these two expressions. So we can just substitute these two expressions here in order to find the value of x of n. So we have this x of k, so this should be x of n. So we have the value of x of n is equal to 1 by n summation k running from 0 to n minus 1. So this x1 of k can be given as summation m running from 0 to n minus 1 x1 of m into e to the power minus j 2 pi km by n. Similarly, this x2 of k can be given as summation L running from 0 to n minus 1 x2 of L into e to the power minus j 2 pi kl by n multiplied by this factor e to the power j 2 pi kn by capital N. So now what we can do is we can just take this factor which is here inside till this point, because we can have these summations here and consider these complex exponents together. So what we get is this summation m running from 0 to n minus 1 x1 of m, then we have this summation L running from 0 to n minus 1 x2 of L, and now we have this factor that is 1 by n multiplied by summation k running from 0 to n minus 1 e to the power minus j 2 pi km by n, then e to the power minus j 2 pi kl by n into e to the power j 2 pi kn by capital N. So this can be written as summation m running from 0 to n minus 1 x1 of m summation L running from 0 to n minus 1 x2 of L multiplied by 1 by n summation k running from 0 to n minus 1 into e to the power, we can take out this j 2 pi k by n outside, and we have n minus m minus L. So we have the value of x of n something like this. So now let us consider this part here and represent it by s. So we have s is equal to summation k running from 0 to n minus 1 e to the power j 2 pi k into n minus L minus m divided by capital N. So let us try evaluating this sum, and for that we will consider two cases. So the case 1 is when this n minus l minus m is an integer multiple of capital N. So let's say it is an integer multiple of capital N. So this p is some integer. So if we substitute this in this expression of s, so we have s is equal to summation k running from 0 to n minus 1 e to the power j 2 pi k into p into capital N divided by n. So this n gets cancelled, which is equal to summation k running from 0 to n minus 1. Now if we observe this factor here, it is e to the power j 2 pi k into p. So it is simply integer multiple of 2 pi, which means that e to the power j into integer multiple of 2 pi has the value of 1. So we have inside this summation 1, and this 1 is being added n times, therefore the value of this sum is given as n. So when we have this factor n minus l minus 1 is equal to pn, that is integer multiple of n, at that time the value of this s is given as n. So now let us consider the second case where this n minus l minus m is not an integer multiple of n. So for that this summation can't be reduced further, so it is given as k running from 0 to n minus 1 e to the power j 2 pi kn by n. So it is n minus m minus l, and this can be written as summation k running from 0 to n minus 1 e to the power j 2 pi into n minus m minus l divided by n whole to the power k. So this resembles summation k running from 0 to n minus 1 a to the power k, and we know that it is given as 1 minus a to the power n divided by 1 minus a. So if we substitute the value of a as this factor, the value of s that we obtain is given as 1 minus this factor e to the power j 2 pi into n minus m minus l divided by n whole to the power n divided by 1 minus e to the power j 2 pi into n minus m minus l divided by n, and this n here and here gets cancelled, and now if we observe here, we are getting 2 pi into n minus m minus l, which means this is again integer multiple of 2 pi, which means this exponent here reduces to 1. So in numerator we are getting 1 minus 1, which means this sum is now reducing to 0. So this s is equal to 0 when we have n minus l minus 1 not an integer multiple of n. So what we have is the value of this s is equal to n if the factor n minus m minus l is an integer multiple of capital N, and it is equal to 0 if this n minus m minus l is not equal to the integer multiple of capital N. So now let us consider this n minus m minus l is equal to Pn, and let us shift this factor n minus m to RHS. So we have minus l is equal to Pn minus n minus m. So what we can observe is we are going to have an impulse every time. So this L can be written as minus of Pn minus n minus m. So we can observe here the value of L, which is given as minus Pn minus n minus m. So we can have this value of P as 0, 1, 2 and 3 and so on, which simply means that if we have n minus m, then we are going to get the value of L, and at this value of n we are going to get the value of sum as n, and this entire term here can be represented as L is equal to n minus m mod n. So this entire term here results into the modulo operation, that is n minus m mod n, which means that when the value of L is given like this, then at that time we are going to get an impulse of n of amplitude n, and otherwise we are going to get 0. So this can be represented as S is equal to n times an impulse located at n minus m mod n, which means that we have an impulse of amplitude n at L equal to n minus m mod n, and for other values it is going to be 0. And now if we substitute this value of n in this expression that is here, so we have it something like this. So this factor n and n gets cancelled, and what we are left with is summation m running from 0 to n minus 1 x1 of m summation L running from 0 to n minus 1 x2 of L into del of L minus n minus m mod n. So now using the shifting property of this unit impulse, this L can be simply replaced by n minus m mod n, and this factor can be taken outside the summation. So what we have is summation m running from 0 to n minus 1 x1 of m into x2 of n minus m mod n into summation L running from 0 to n minus 1 del of L minus n minus m mod n. Now we know that this L is ranging from 0 to n minus 1, and this n minus m mod n is going to give us the value which is lower than such that this L minus n minus m mod n will be within the range from 0 to n minus 1, which means that if we just add all the values in this range, so this summation is going to give us the value 1, and therefore this x of n is given as summation m running from 0 to n minus 1 x1 of m into x2 of n minus m mod n. So we have the value of x of n something like this. Now this resembles a known equation, that is, if we consider the value of x1 of n being convolved with x2 of n, so we know that it is given as summation m running from minus infinity to infinity x1 of m multiplied by x2 of n minus m. So if we compare these two equations, we observe that in this expression that we have obtained, we have m equal to 0 to n minus 1, and this x1 of m is as it is, and this x2 of n is having this modulo n operation, means the after flipping and shifting we are having this modulo n operation which is not present here. So the expression that we are having here is the linear convolution Now what does this modulo operation do? So when we consider this n minus m mod n, instead of having the shifts linearly, we are going to get the shifts in a circular fashion. So therefore, due to this circular shifts, this expression is known as circular convolution. Therefore, this expression, that is x of n, is circular convolution, and it is given as x of n circularly convolved with x2 of n. So this is the symbol for circular convolution. So what we can conclude is, when we have x1 of n circularly convolved with x2 of n, at that time its endpoint DFT is given as x1 of k multiplied by x2 of k. So when we have multiplication in the frequency domain, so at that time we are getting the circular convolution in the time domain. But when we had the case when we were having x1 of omega being multiplied by x2 of omega, at that time instead of having this circular convolution, we were having the linear convolution. So this is circular convolution, and this is linear convolution. And we have seen that the difference between these two expressions is that instead of having an infinite range of m, we are having the range of m as 0 to n minus 1, and instead of having linear shifts, that is shifting the value of this n linearly, we are having circular shifts, that is we are shifting the value of this n in a circular fashion. So in this lecture, we have introduced the concept of the circular convolution, and we saw that when we have multiplication in frequency domain, that is x1 of k into x2 of k, at that time we are having circular convolution in the time domain, that is x1 of n circularly convolved with x2 of n, and the expression for this circular convolution is given as m equal to 0 to n minus 1 x1 of m into x2 of n minus m mod n. And we know that instead of having linear shifts as in linear convolution, we are having circular shifts of n in the circular convolution. In the next lecture, we will look at a simple example in order to find the circular convolution. Till then, let's stop here. Thank you.